LLM writes code in production. Sandbox it, or it will eventually bite you. You will leave this video able to run tool-generated Python with clear safety layers, so untrusted code cannot steal data or fork your process. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. People hand-generated code to tools because it automates work. That convenience brings risk. Unchecked code can open files, run external programs, or leak secrets. For data scientists, that risk shows up as corrupted datasets, surprise compute spikes, or worse, production incidents that are hard to trace. Safe execution is the set of patterns that keeps tool-generated Python useful while limiting those dangers. Success looks like predictable outputs, bounded resource use, and no hidden channels for exfiltration. At a high level, safe execution means three things. First, execute untrusted source only after you vet its surface. Second, run it in a reduced runtime that lacks dangerous built-ins. Third, expose only small host helpers that do one narrow task. A tiny example is running a short snippet that computes a top 2 list from a shared array, while the environment disallows importing or opening files. The strengths are fast feedback and clear audit points. The weakness is you must design your helpers carefully so they do not themselves become attack vectors. We will build a minimal sandboxed flow. It shows how to compile and run a short tool program safely, block imports, provide a single host helper for ranking, clamp its outputs, and add a simple validator that rejects risky tokens before execution. This gives you an actionable baseline you can expand for notebooks, APIs, or batch jobs. Now, we'll compile and run a sandboxed program. This snippet safely compiles and runs a tiny tool program with RestrictedPython. The variable code holds untrusted Python that doubles each value in nums and stores the total in result. The dictionary env supplies an allowlisted runtime where builtins is set to safe builtins, blocking dangerous capabilities by default. The function compile_restricted transforms the string into bytecode that enforces restricted Python rules. An exec runs it with env globals and loc locals. The variable loc then contains the computed result for inspection. The printed sandbox sum confirms the code executed inside the sandbox with only approved built-ins and data. This flow shows the core idea. Convert source to restricted bytecode, run it in a tiny allow list, and then check the outcome from the host. Next, we'll show how imports are denied in the sandbox. This example demonstrates RestrictedPython denying imports inside untrusted code. The string code attempts import OS. Because env uses safe built-ins without import, the import fails under the sandbox. A bare except keeps B true when the import is blocked, and result captures that outcome. The function compile_restricted compiles this code under RestrictedPython, and exec executes it with the same allowlisted environment. The printed imports blocked true indicates import attempts are neutralized, which reduces exfiltration and process spawning risks. This pattern is important because import is a common route to system calls and file access. So removing import from built-ins neutralizes large classes of attack. Next, we'll expose a single allowlisted helper from the host. This code lets sandboxed code call an allowlisted helper via RestrictedPython. The function topk sorts a list and returns the topk values. It runs in the host and is intentionally narrow in scope. Adding topk to env exposes only this safe primitive to untrusted code. The code string calls topk on the shared nums data. and compile restricted with exec executes it under the same restricted built-ins. The variable loc receives the selected values. The printed top2 shows a ranked selection performed through a strictly allowlisted function, not arbitrary operations. That separation keeps heavy logic in safe host code while letting the sandbox orchestrate simple coordination. Next, we'll clamp what the helper can return, so the sandbox cannot ask for unlimited results. This snippet enforces a cap on selection size inside the RestrictedPython sandbox. The integer kmax defines a global ceiling, and the helper gate k clamps any requested k to that limit. Exposing gate k and kmax in env ensures tool-generated code must pass through the clamp to reach topk. The string code asks for 3 items, but gate k reduces it to 2 before topk runs. If you increase kmax, more items are returned. Decreasing kmax lowers latency and memory by shrinking outputs. The printed k_used shows clamping worked, proving the code cannot exceed your configured bound. This pattern moves a simple policy decision into the host, where you can tune it for latency or cost. Next, we'll add a quick validator that rejects risky source before compilation. This example adds a quick pre-execution validator to RestrictedPython for extra safety. The set deny lists risky tokens like import, _, and open, and the expression with all rejects any source containing them by swapping in a benign fallback. The code string still invokes gate k, so the earlier kmax limit remains enforced before topk runs. The call to compile restricted and exec then runs only validated code in the allowlisted env. The printed final all_n confirms both the validation and the hard selection limit took effect, forming a tiny but complete safe execution baseline. That validator is cheap and catches blunt attempts to use forbidden constructs before you do any compile work. If you lift this toy example to real work, treat the helper functions as a small API surface. Keep each helper single purpose. Log each execution and the values returned. Measure time and memory in the host and fail fast on outliers. That way, you maintain observability and a clear audit trail for any tool-generated action. Recap. What it is: a tiny sandbox that compiles and runs untrusted Python under RestrictedPython with allowlisted built-ins. When to use it? Whenever you run model or tool-generated code that must not access files, spawn processes, or leak secrets. One caveat: restricted runtimes are not a silver bullet. Every exposed helper is a potential attack surface and must be minimal and audited. Next step: pick one parameter and tune it for your needs. For example, change the selection cap so kmax matches your latency and memory budget. Then run a few empirical checks on larger arrays to measure impact. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.